Hi. So far in the course, we have seen various methods for showing concentration bounds. We have seen the basic Chernoff method where tensorization plays an important role. And we saw various ways in which tensorization can be shown, starting with the bounded difference property and how it leads to tensorization. And we moved on to some more abstract methods, which are in some sense more powerful, where we showed the entropy method and the transportation method. In the entropy method, we use this argument called Herbst argument, which gives an alternative formula for log moment generating function in terms of divergence. And in this method, the main technical tool that is used to show concentration bounds is this so-called log Sobolev inequality. We established three different log Sobolev inequalities. We established one for the case of binary random for case of random variable distributed uniformly over plus minus one valued vectors of length n or d. Then we saw the Gaussian log Sobolev inequality, and then we see a more general modified log Sobolev inequality, which allowed us to derive concentration bounds for an arbitrary random variable. Uh, for the next 2 to 3 weeks, I will be focusing on this log Sobolev inequality. And what I will show is I will show how this log Sobolev inequality is connected to other inequalities that have a longer history, perhaps, and that are not directly similar. If you look at it, you won't see the similarity, but you will see very interestingly that many of these inequalities are related to this log Sobolev inequality. So we will start with the connection between log Sobolev inequality, the Gaussian log Sobolev inequality, and so-called Stams inequality. So let's begin. So let's first recall the Gaussian log Sobolev inequality in its general form that we saw. So I'll just abbreviate log Sobolev inequality by this LSI. These three. This is LSI stands for log Sobolev inequality. So the Gaussian LSI that we saw was the following. Suppose X is a Gaussian random variable with mean 0 and identity equivariance matrix, and and let f be a function from Rn to R such that it satisfies two properties. This function f satisfies two properties. First is that this function has finite second moment, and second that the entropy of f square is second that this function is continuously differentiable. Okay, and let's say its derivative is and also let's say it has a compact support. Okay, so suppose you have such a function, and given this function we have a bound on its entropy of f square. Remember, entropy can be defined only for non-negative functions, so we just take a square here. Is this entropy is less than equal to expected value of this function is differentiable, so we can talk about its gradient. So this gradient is a vector of length n, and we take the 2 norm of this vector, and this is the inequality. This is the log Sobolev inequality. Okay. Okay. This is the Gaussian log Sobolev inequality. We presented a proof of this inequality where we first derived the binary log Sobolev inequality, and then we use central limit theorem to derive the Gaussian log Sobolev inequality. Now, one important property that we used in all these proofs is the tensorization property, which essentially tells us that uh, it suffices to show this inequality for n equal to 1 for the one-dimensional case. So the inequality above holds if and only if it holds for n equal to 1. So if this inequality holds for all functions for n equal to 1, then it must hold for uh, all functions for larger n. Okay, that's the result. This to show this result, we use the tensorization property of entropy. In other words, the inequality that we showed was the following. So we can now think of just a single Gaussian random variable with mean 0 and variance 1, and consider a function f from R to R such that it satisfies two properties. One, that it has finite variance, and second, that this function f belongs to, again, same as before, except that the domain is now R instead of Rn. Okay. Suppose we have these two properties, then we have, again, this is the one-dimensional version. Entropy f square is less than equal to 2 expected value. So we can just talk about the derivative, because now we are talking about functions on R. This was the second form that we this was the simplified inequality that we actually showed, and it is very important that we could reduce our original inequality to this one-dimensional version, and this is what we said was that this is an elementary inequality. It involves few random variables, few parameters, especially for the binary case, and therefore it can be directly verified. Okay. Next, what we observe is that we can even further relax the requirement. We make the following observation, that for a function f from R to R and any distribution x such that, let's say, the entropy exists. So function is uh, let's say the function is non-negative. Well, we'll take f squared such that entropy, such that this is finite, the second moment is finite. The entropy of uh, so consider this function f, and now consider another function, let's call it f bar of x, which is just a times f of x. So this is the definition. Then entropy of uh, f bar square is equal to, this is something you can easily check, is equal to a square times entropy of f square. And clearly the gradient of f bar is equal to a times gradient of f. Okay. And therefore it suffices to consider functions f with, we can normalize them, expected value of f square equal to 1. Okay, we just said expected, earlier we were saying expected value of f square is finite, but we can always normalize a function, the inequality doesn't change. Okay, so we will, that's another equivalent form. So what I'm saying here is that in the second form here, we might as well just require expected value of f square equal to 1. Okay, so basically the form we have is that uh, for every, yeah, need not write it again. So it's the same as this previous one, except that we have expected value of square equal to 1. That's the third form. That one suffices. Okay. So now that we have this simplification, we'll provide a slightly different looking form. Okay. So suppose you have a function f from R to R such that f is continuously differentiable and expected value of f square is 1, okay, where x is the standard Gaussian random variable, standard normal random variable. Suppose you have such a function. So we'll define a new probability measure. Let p be the Gaussian measure. So let p be this Gaussian measure and define q that has a density with respect to p by, so it's given by, we can just, since it has density with respect to p, we can just describe the density. The density is given by, let's say, f square. Okay, that's the definition of q. So q is absolutely continuous with respect to p, which means it has a density with respect to p, and the density is the same as f square. So if you look at such a q, then is something we had seen earlier, then the divergence between q and p is exactly equal to the entropy of f square. Okay, right. Okay, so this is saying that the left side of log Sobolev inequality that we want to prove can be expressed as entropy of can be expressed as a divergence between q and p. But what about the right side? So does the right side of LSI in 3 have any meaning here? So we saw that the left side is just the divergence. Here the left side is just the divergence. What about the right side? So it turns out that in fact right side also is a rather interesting quantity. Okay, and we will tell what that is. So here is the idea. So what we do is, let's say let gx be just f square. Then if you look at the derivative of fx, we might as well assume that f is non-negative because we only work with we only work with f square here. Okay, and then we take a mod of the gradient, so we just might as well just assume that f square is non-negative, f is non-negative. So this guy is the same as derivative of square root of gx, which is the same as 1 by 2 gx g prime x, right? And therefore the right side of LSI, which was expected value of the derivative of f square. So this term which appears on the right side, there's a factor of 2 appears on the right side. This is equal to expected value. So we take this square here. So this becomes g prime x square, and we get 1 by 4 gx. But this can also be written as expected value of, let me take this 1 by 4 outside, expected value of gx times, so you get g prime x square by gx square because there was just dx, I multiply and divide by gx. So what is g prime by gx whole square? Well, that's just the derivative of log of gx. Okay, so I'm using this notation, the derivative of log of gx whole square. Okay, and in fact this g is the density of q with respect to p. All these expectations are with respect to the Gaussian measure p, and when you multiply it with density, which is something we discussed earlier about Radon-Nikodym derivatives or densities, this makes it expectation with respect to q of this guy. Okay, right. So we can view it as follows. This guy here is expected value with respect to q of the derivative of log density of q with respect to p whole square. Just for comparison, recall that Kullback-Leibler divergence of q with respect to p is the expected value with respect to q of log of density. Okay, and this guy now looks like the derivative of log of density whole square. So this, in that sense, this looks also like some measure of divergence between q and p. And in fact, this is also a well-studied measure, and it has a name. Okay, so we will call this thing the quantity EQ, expected value with respect to q of derivative of log likelihood ratio of q with respect to p square, is called the relative Fisher information. And of q with respect to p. So to even talk about this relative Fisher information, we must q must have a density with respect to p, and the density must be differentiable. Only then we can talk about this relative Fisher information. And perhaps a better name would be Fisher divergence. Then it would then you can easily draw a parallel between Kullback-Leibler divergence and this Fisher divergence. Okay, so it turns out that this quantity on the right also, the quantity that we saw on the right, also is also looks like a standard quantity. So to summarize, we to have the general Gaussian log-Sobolev inequality, it suffices to show this is equivalent, exactly equivalent to the general log-Sobolev inequality. It suffices to show that dqp is less than equal to, so there's a factor of 2, but there's a 1/4 here, half, okay, sorry, one notation here. This relative Fisher information is denoted as I of qp. So it suffices. So basically, what the log-Sobolev inequality we're after is exactly equivalent to saying dqp is less than equal to half of iqp. Very similar to Pinsker's inequality. Okay, except that now you're showing it for divergence and showing that divergence is in turn less than equal to half of some other notion of distance, this relative Fisher information distance. And we need to show this for every q that has a density with respect to p, that's absolutely continuous with respect to p, and such that its density is differentiable. Okay, so any q that has a continuously differentiable entropy with respect to p, if we show that it satisfies dqp less than equal to half iqp, and here p is the Gaussian measure, then we'll have the Gaussian log-Sobolev inequality. Okay, just to insist that p is the Gaussian measure, I'll just put pg instead of just p. Pg, standard Gaussian measure. Okay. So pg. Okay. By the way, just a quick fact. having density with respect to Gaussian is equivalent to having the standard density. Okay, and that's equivalent. You can show that. So a measure is absolutely continuous with respect to the Gaussian measure if and only if it's absolutely continuous with respect to the Lebesgue measure, the standard measure that we use for integration. And in fact, the density with respect to Gaussian will be given by the standard density divided by the Gaussian density. Okay, so this log likelihood ratio, this density with respect to Gaussian Gaussian is just the likelihood ratio. All right. So now we see a different form of log Sobolev inequality. The amazing thing here is that it was a dry inequality, not having so much meaning, and now suddenly it looks like we are talking about sort of relation between two different notion of distances between distribution. So you have a Gaussian distribution and this Q which is slightly away from Gaussian distribution. Then we want to claim that the divergence between Q and PG is less than or equal to half times relative Fisher information between Q and PG. Okay, that's what we wanted to show. Indeed, we have already shown this. This lecture is about showing different equivalent forms of the same inequality. All right. Okay. In fact, we have seen now 4 different equivalent forms. We are continuously simplifying the original inequality. So in fact, there's another equivalent form. We can do another rescaling. So observe that entropy of f square x is less than equal to 2 times expected value of f prime x square for all f that are continuously differentiable with expected value of f square equal to 1. Or let's say finite, instead of a more convenient form, where for x distributed as standard normal, this inequality holds if and only if it holds so now I'm trying a different random variable here. If this guy holds for all f okay, I'm changing x to x bar. For now, we'll use a different distribution for x bar that has Gaussian 0 mean and variance s. Okay, this is easy to see. You just rescale x to x by s. So multiply and divide x with s and use sx as x bar. But the function changes from f of x to f of x by s. Okay, that's the new function. But it holds for all functions, so that's why you get this equivalence. It's just a simple rescaling argument. So it suffices to verify this inequality for s equal to 1, but once you get it for s equal to 1, you get it for all s. Okay. So our log Sobolev inequality is equivalent to the following. Thus, our SI is equivalent to the following: dqpg is less than equal to s by 2 iq pg for all q that have density with respect to Gaussian, such that the density is this is differential. Sorry, this is not density with respect to Gaussian. This is density with respect to a Gaussian with variance s. Okay. So PGS is a Gaussian with zero mean and variances. Okay. Okay, this is the log Sobolev inequality that we have already shown. All right. Okay, so far so good. So if it holds for s equal to 1, it holds for every s greater than 0. Okay. Now what we will do is we will see another equivalent form. We have seen so many equivalent forms. Now we are at this form 5. Now we'll see a final equivalent form, which is form 6. Okay, I'll just call it form 6. So what is this 6? So let's consider Q okay. Let's say the Q let's consider Q that has differentiable density Q. Okay. So then if you assume this about Q, this implies Q is absolutely continuous with respect to GS for any s greater than 0 and has differentiable density with respect to GS as well. Okay, in fact, this density with respect to GS is the ratio of QX by Gaussian density. Okay. So what is dq PGS? This is equal to Q of X. So this integral is from minus infinity to infinity over the real line log Q of X by this gamma Sx. Okay, this gamma Xx is the Gaussian density. So this is density of Gaussian N0 S. Okay, so that's what this is, and we can expand the log. So this Gaussian density we can write as we know what this is, e to the power minus x square by 2s divided by root 2 pi s. Correct. So when we substitute that and take this log here, what we get is half log 2 pi s plus expected value under q of x square by 2s. This is for this denominator part. And then minus so this quantity that we see here, if you have not seen it before, is sort of an entropy. Just like Shannon entropy captures cardinalities of large probability sets, this is what is called differential entropy. And it sort of captures the volumes of large probability sets. Okay, so you may not even worry about this operational significance of this differential entropy and just view it as some quantity. Okay, this formula here, differential entropy. Okay, so you have this differential entropy, and let's also assume an assumption that expected value under q of x square, which appears here, is finite. Okay, that's an assumption that we make. Okay. So this guy is just this. Therefore, okay, so we've already seen this. So dqp that we have here is half log 2 pi s plus eqx square by 2s minus differential entropy of q. Okay, that's what dqp is. That's what the left side of our log Sobolev inequality is. What about the right side? Let's see further. If you look at the right side, I of qpgs, which we said was equal to expected value with respect to q of the derivative of the density whole square. The density here is qx by gamma sx. Its derivative of its log is so let's do the derivative of its log. So that's the derivative of qx, right, plus the derivative of log of Gaussian. So log of Gaussian is just minus x square, minus the derivative of log of Gaussian. So log of Gaussian is minus x square by 2s here, and its derivative is 2x by 2s, minus 2x by 2s, and so that 2 cancels, and so all you get here is x by s. Okay, this whole square expected value with respect to q. Okay, so we can expand this whole thing. This can be written as expected value over q of this quantity. This is log of density. The Gaussian part of the density has now disappeared. This is log of the standard Lebesgue density plus this guy here, expected value under q of x square by s, and plus 2 by s into expected value under q of x times this guy. Okay, so let's look at this last term here. This is the expression for information. Note that we'll multiply this with s by 2 for our inequality. So this term here, sorry, there is no by s square, yeah, by s square. So when we multiply this with s by 2, we see what we see on this side. Okay, so this term will cancel on both sides of inequality. Okay, let's look at the last term. What is this term? The last term it can be simplified further. Can be simplified as expected value over q of x times this. This is equal to, I'll write, let's say for simplicity, let's just write the whole integral. Qx x d by dx ln qx dx. Now, we can do integration by part. Okay. Actually, even before that, this we can write this derivative of log qx as q prime x by qx. So this looks like this to infinity x qx q prime x, because q is differentiable, by qx dx. So this term goes away. And then this becomes now when we use integral by part, we take this as the first part and this is the second part. So this becomes x qx minus infinity infinity, two limits we have to take, minus qx dx. So now what is this second term? This is a density, and we integrate the density, so that's just minus 1. So this term is just minus 1. What about this first term? this term is 0. Okay, and the reason why this term can be seen to be 0 is because of an assumption that we made. The fact that this first term is 0 can be seen as follows. So we have assumed that expected value under q of x square, we've assumed that this guy is finite, but this second moment always exceeds first moment, and therefore this is finite, and therefore if you take, this is by the way the integral minus infinity to infinity qx mod x dx, and therefore in the limit as x goes to infinity, both qx and both qx in both the limits as x go to infinity and minus infinity, qx mod x must be 0, and therefore both these terms are 0, so this becomes 0. Okay, so basically this term, this x derivative of log qx, this looks so formidable, but this is just minus 1. Okay, so this last term here in this expression is just minus 1. So to summarize, what we have shown is that this information, this relative Fisher information is equal to this plus expected value under q of x square by s square minus 2s. Yeah, I think it's minus 2 over s. Minus 2 over s. Okay, so this is this term, and the first term divergence was this one here. Let me just zoom out so that we can see both of them at the same time, hopefully. Right. Okay, so you see s by 2 here, you see log s by 2 here, this term here, and we see this term here, right? So this implies therefore dqpg is less than equal to s by 2 I qpg if and only if this time thing cancels here. If you do s by 2, this is same as this, so this guy cancels. This is minus hq this. So what we get is if and only if half ln 2 pi s minus hq is less than equal to s by 2, this guy here, eq of minus 1. Okay, that's the equivalent form that we can have. Okay, so this is the equivalent form that we can have. This is exactly equal to log Sobolev inequality. Alright, so now what we will do is we'll take all the s related term on the same side and get the other terms on the other side. So what do we get? By the way, this is minus s by 2. Right, that's minus 1. Right, so this is the same as we have the following equivalent form of LSI. Okay, so what is this equivalent form? It says half ln 2 pi minus h of q plus 1, because there was a minus 1 on that side that I brought here, is less than equal to s, take this half out, s expected value under q of this expression here, ln qx whole square, minus ln s. This is this ln s here. Okay. And this must hold for all s greater than 0. So this is true if and only if half ln 2 pi minus hq plus 1 is less than equal to half smallest value, the infimum over s of this guy, minus ln s. So what's the infimum over s? We can just take the derivative. So when you take the derivative, this is 1 by s and this is this, so that it's attained for s equal to 1 by this. Okay. So when you put s equal to 1 by this, what you get is equals to half of 1 plus ln expected value over q. Okay, that's the inequality which we get, right? And so now we rearrange the terms. We get half on this side. And what we get, so we first subtract half from this one and then we take this factor of half here. So what it says is that half, so ln 2 pi e minus 2 hq is less than equal to ln expected value over q, this derivative qx whole square. Okay, that is, so we will change some things and take it on this side. So that is the same as saying that 1 is less than equal to expected value of this. This is this term, and the second term is e to the power 2hq divided by 2 pi e. Okay, that's the second term. Okay, so these are two terms which look sort of not defined. In fact, these two terms have a rich history. This is the so-called entropy power of q. Okay, entropy power of the BMF q. Oh, sorry, of the density q. Okay, and it's denoted by nq. It's used quite a bit in information theory, especially for Gaussian channels. For example, a basic inequality used to show converse bound for Gaussian channel is called the entropy power inequality, which says that n of q1, n of x1 plus x2 exceeds n of x1 plus n of x2. Okay, that's the entropy power inequality. And this term here actually also has a name. This is the derivative of the log likelihoods. This thing is called the score function. And so we are looking at the first thing to check is that this expected value of the score function is actually 0. Okay, under some regularity conditions, expected value of the score function is 0. Actually, we already use some regularity conditions here. No. So yeah, the expected value of the score function is 0, and therefore this is just the variance of the score function. And so this thing is called the Fisher information of the distribution Q. Okay, so Fisher information of um, Fisher information of Q. So unlike the typical Fisher information that we use in sort of these inequalities called Kramer-Rao bound or Ventry's inequality, this is a Fisher information of a prior, which also comes up in Ventry's inequality actually, and that prior is Q here. So this is a Fisher information of Q. So you can associate this Fisher information with any probability measure Q with a differentiable density. Okay, so what this inequality here is saying is that 1 is less than JQ times NQ. Okay, so JQ times NQ is greater than 1. This is sort of an uncertainty principle. It says that both Fisher information for Q and entropy power for Q cannot be small at the same time. And in fact, this, as we saw, that this inequality is exactly equivalent to log Sobolev inequality, and this is called Stams inequality. Okay. And it's from 1959, and the LSI, this Gaussian LSI, is due to Gross from 1975. But Gross didn't know, most very likely, that this inequality existed. This Stams inequality existed, which was exactly equivalent to log Sobolev inequality. I think this equivalence was shown only in early 90s. Okay. So so we have shown that log Sobolev inequality is equivalent to this Stams inequality. We have already given a proof for Gaussian log Sobolev inequality, and therefore we have already established this Stams inequality. Okay. So yeah, the Stams inequality holds because log Sobolev inequality holds. So now that we have seen this equivalence between Stams inequality and the log Sobolev inequality for n equal to 1, which we already saw was equivalent to the general log Sobolev inequality, in the next lecture we will prove this Stams inequality not using sort of central limit theorem and binary log Sobolev inequality, which we did earlier, but directly using some information theoretic method. In fact, we will use the operational significance of these quantities JQ and NQ, and hopefully we'll be able to give more heuristic meaning to this inequality. Earlier, the proof of log Sobolev inequality in some sense was a technical proof, just showing some mechanics, techniques involved in the proof, but now hopefully we'll be able to give more meaning to it. And that's what we'll do in the next lecture. We will prove Stams inequality. See you in the next lecture.